My screen is visible, ma'am?
Yeah, it's visible.
PPT?
Yes, sir, it is visible.
Okay, okay. So there is some technical problem from the expert end. So shortly he is going to join.
Okay.
Sir, voice is not coming. Hello.
Hello. Sir, actually, the presentation has not been
Acha,
started yet.
presentation is just to be started.
Yeah.
At what time it will be starting?
The time was scheduled at 11 o'clock, but due to some technical problems from the speaker side, so it is
Hmm.
getting delayed. So kindly wait for some more time.
Okay, okay, ma'am.
Okay.
Okay, thank you.
Okay.
Good morning, sir.
Hello, good morning. So,
Hello, sir.
am I
How are you?
audible?
Yes, sir. Yes, sir. You are audible. My screen
Oh,
is
okay.
visible to
Thank
you.
you. Yeah, visible. Yes.
Okay. So shall I start, sir?
Can it be full screen? No.
Yes, sir. Sure. I'll do it. Satya, ma'am.
Yes, sir. We can
Okay.
start. Very good morning to all. It's my immense pleasure to welcome our today's eminent speaker, Professor N. Sukavanam from Department of Mathematics, IIT Roorkee. Good morning, sir. Myself,
Good
Dr.
morning.
Satya, one of the coordinators.
Hello.
It's my privilege to give a brief introduction about our today's speaker. Professor N. Sukavanam completed his BSc degree in Maths Physics Statistics in University of Madras in 1977 and MSc Mathematics in University of Madras in 1979 and completed his doctoral degree from ISA Bangalore in 1985. He has worked as Scientist B in Naval Science and Technological Laboratory DRDO, Vizag during 1984 to 86 and as a research scientist in IIT Bombay during 1987 to 1990 and lecturer in BITS Pilani during 1990 to 96 and then he joined as an assistant professor in Department of Mathematics IIT Roorkee and there he has been serving as professor since 2012. Professor Sugavanam has supervised 19 doctoral thesis works and 6 are in progress and guided 50 MSc, MPhil, MCA dissertations. He has worked in various sponsored research projects and coordinated different courses and also developed different courses such as mathematical control theory, robotics and control, NPTEL course on dynamical systems and control, and he has published more than 120 journals, research articles in national, international and national of repute. His area of research includes nonlinear analysis, control theory and robotics and control. Now I may request our respected speaker to kindly start the session. Please, sir.
Okay, thank you, madam.
Thank you, sir.
First of all, I thank Professor Afzal Sikandar for inviting me for this short-term course on optimization and control design techniques. So when I was asked to give a lecture in this one, I thought it will be suitable to give control on robotics. So control techniques applied for controlling robot manipulators and biped robots. So that is how I selected this particular topic. I hope it will be useful for the audience who are pursuing design techniques or applied in the area of robotics. So this lecture will give most of the fundamental concepts which we used to study in a robotics course. In that way, I have planned this. Next slide, please. Okay. So robotics is an interdisciplinary area, as we all know, because a particular subject is not dealt in this: electrical, electronics, mechanical, or computer science, mathematics, all are involved in this area. So it is a purely interdisciplinary area, and a robot is a machine which is imbibed with some intelligence. So the intelligence comes from various devices like the sensors, various sensor, vision sensor or tactile sensor, etc., attached at various positions of a robot manipulator. So robot may be a humanoid type of robot, or it is a simple machine which is used for pick and place in a factory situation or etc. So that is the robot definition is it is a machine imbibed with artificial intelligence which can take its own decision at various levels. Okay. So next slide, please. And here it is showing a simple robot, humanoid robot, and its components are the manipulator, means the body, main body structure, and actuators are all placed at various joints of the robot manipulator. Effectors means the end of, for example, the wrist and fingers, or we can say the feet of the robot. These are all the end effectors of the robot. Sensors, we know various sensors can be attached. The position sensor, velocity sensor, or vision sensor, and so many other things can be added to give a artificial intelligence. And controller is the utilizing the information coming from sensors, how the robot is trained to perform a various given task in an intelligent manner by taking its own decisions. That is how the optimization and control comes into picture. So there some mathematical techniques and various softwares can be used for controlling a robot manipulator. So next one, please. So here, this video shows, I think this can be skipped. It is just a walking robot manipulator. And we know that to perform a simple job of walking a few steps, it involves a lot of things. Okay, combination of so many softwares and a lot of mathematical techniques, everything is involved. Sensors, information, big data analysis, all combined together only can make a robot walk like this. So next slide, please. So here the manipulator is the main body and it has different configurations. So we can see here P indicates prismatic, R indicates revolute. So prismatic joint of a robot, it means it will move backward and forward in a straight line motion only. So if a link of a manipulator moves backward, forward, it is the joint making that motion is called prismatic joint. And if it is rotating, the joint making that rotation is called the revolute joint. So any robot is made up of many prismatic and many revolute joints. So if 3 prismatic joints are there in this type of robot, then it is Cartesian, and then cylindrical, it means 2 revolute and 1 prismatic. Here RPP, 2 prismatic joint. So we can see that this rotation makes a circle and the prismatic joints move it back, forward and backward, or up and down. So it will form a cylindrical volume after, if you take into account the all positions of the end of the manipulator, the hand, then it will form a volume that is a cylinder. So we can call it a cylindrical manipulator. Here spherical means it has 2 revolute and 1 prismatic. So it will rotate like this. It will make a sphere. The 2 revolute joint will make it as a sphere, and prismatic joint will move the end effector backward and forward. So it will form the volume of a spherical shape. So like that we have various types of manipulator in this as depicted here. So next slide, please. So the end effector means the end of the robot, the fingers and tools. You can say it is called grippers or tools. So this can hold an object and place it in some other place, or there can be sharp-edged tools kept on the end effector so that it will be like a screwdriver or some kind of spanner, etc. can be held in the end effector. So normally it is called gripper or tools, and okay. So it is also a part of the robot manipulator. Okay. Next one, please. Yeah, is it visible full screen? Yeah. Okay. So here also it is showing the joints. Again, the same description. Prismatic is going forward and backward here, and the spherical joint has 3 rotation at the same place. So you can say that it is a rotation about x-axis, y-axis, z-axis kept at one place. In other words, 3 actuators situated at one particular joint that will make the spherical motion of the joint, of the link. Okay. Yeah, next one, please. So this video, it will show various videos are available in the internet. One can easily take so many of them, but this one shows how intricate work is done by a robot manipulator. it's it has a link, several links like this, and several joints here, revolute joints, all of them. And the end effector is the gripper, and it grips the object, and it is taking it from one place and keeping it in another place. The complicated orientations are there here. The environment is a bit complicated. It has to plan its path properly, where to take the object, first of all, and then in which orientation the hand should be kept so that it is taken safely, and then keeping it at the particular position. So this move, even though it is very trivial for a human being, it is not so trivial to make a machine to do like this. So it needs a lot of planning. The control techniques are to be applied for making the robot do this one. Okay, next slide, please. So here the degree of freedom is the number of variables. The degree of freedom here, it is given that the number of the independent position variables that are required to identify various parts of the robot manipulator. So for example, if a robot is moving only on a planar surface, then we say that there are two rotation is required, and there are two directions, XY direction, and one rotation is required to cover the entire planar surface, isn't it? Because we can, if X and Y are the axis we consider for a plane, X axis and Y axis, then Z axis is perpendicular to that. So if a rotation about the Z axis will make the link move on the XY plane. So one rotation is required, and for placing various objects, we need XY coordinates. So two position variable and one rotation variable is required. So 3 degree of freedom is required for an object to move in various ways on a plane. But if it needs to move freely on a 3-dimensional space, it requires 3 rotations and 3 translation motion. 3 position variables are required. X, Y, Z position, and then rotation about the X axis, Y axis, Z axis is required for a free motion of a rigid body in the space. So the degree of freedom is decided by various joints available on a robot manipulator. So we call it as 3 degree, 4 degree of freedom, etc., depending on the number of joints available on a robot manipulator. But if there are 2 revolute joints which are rotating about the same axis, then both of them are performing the same work. So even though there are 2 revolute joints, it rotating about the same axis, so we cannot call it as 2 degree of freedom, because both of them are doing the same type of rotation. So we will call in that case only 1 degree of freedom. But if 2 rotations are there about 2 different axes, then we call it as 2 degree of freedom, or using the number of joints available, we can call it. So that those examples we will see in various slides. So next slide, please. So here, this is called the reference frame. Because when in the previous video, we have seen that a robot is performing a task of taking an object and placing it one place to another place. So for doing that, first of all, the end effector, the end of the fingers should know where the object is placed. and in which orientation it is placed. For knowing that, it requires a coordinate frame, a X, Y, Z coordinate frame in which the object is placed should be fixed first of all, and we should also, the robot also should know where its hand is placed in the same space. So we need a reference frame, coordinate frame, that is called world reference frame. But whichever frame we are having it as a fixed one, we call it as world reference. Then joint reference frame. So at each joint of the robot, a reference coordinate frame will be fixed, right? So various coordinate systems are, one is a fixed reference frame, that is the world reference frame, and then at each joint of a robot, we will fix a coordinate frame. They are called joint reference frame. Then the tool reference frame is the coordinate frame which is fixed at the end of the robot, at the end effector. And all this, both of them are moving. The joint reference frame will move as the joints are moving. Similarly, the tool reference frame will also move as and when a rotation is made or translation is made at various joints. So all these coordinate frames will be keep on moving when the robot is moving with reference to the world reference frame. Yeah, so the next one, next slide. Yeah. So the workspace of the manipulator is the simple definition that the workspace is the one the volume in the world reference frame, the volume in which the end effector moves. So wherever the end effector moves, we note that as a point X, Y, Z, and the collection of all end effector position will form a volume that is called the workspace of the manipulator. So calculating the workspace of a complicated manipulator may be very difficult because of the various shapes. But if you have three revolute joint or three prismatic joint, we can say that it will look like yes, please. So if there are three prismatic joints, then we can say that it will look like a box. The end effector can move in a cuboid type of space. Similarly, if there are three rotations, then we can say that the end effector can move inside a spherical volume. So these workspaces are very easy to calculate roughly, but in general, we may not be able to compute the workspace, but a rough shape of that will be useful. In real life situation, a robot need not know the exact shape of the workspace, but an approximate, because we should know that whether we can reach a particular point or not. That is the requirement. So if you know that you will be able to reach a particular point, then only we will start controlling, isn't it? If our hand is capable of moving up to 1 meter, and if you are sitting in one position, then there is no point in trying to take an object some 2 meters away, isn't it? So we should know that how far our hand can reach. So that is called the workspace of the manipulator. And once we know that we will be able to reach that particular position and orientation, we will try to control the joints of the robot and then reach that particular object. So that is the purpose of a rough calculation of the workspace. Okay. Yeah. So next slide, please. So the standard terminology of a robotics subject is first we should know various types of robot manipulator, and the direct kinematics. It is a equation relating the position and orientation and of the various joints of the manipulator. We can write a equation relating the end effector position in Cartesian coordinate as well as the joint at various angles at the joints, how they are related. The end effector position as well as the joint variables are related. That relation is called kinematics equation. Then inverse kinematics is the equation, the solution of the kinematics equation. That is, given a end effector position, what are the possible angles of the actuators? So calculating the joint variables for a given end effector position is called the inverse kinematics. So that is required in a practical situation. Okay, that we will see in the next one. Then the trajectory planning. So once we know the position of a previous slide. Yeah. Once we know the position of the object, then we want to reach that object. We have to plan a trajectory, how to reach that object, in which path, because there are infinitely many paths available from the end effector to the object. So one particular path should be selected properly, and then we have to control the robot. That is called the trajectory planning. And then the differential motion, the velocity should be controlled. Once we decide a path, at what velocity the hand should move, that is the differential relation will give that information. And then the next one is the manipulator dynamics. The dynamics equation is the force and torque applied at each joint of the robot manipulator. So that relation, the equation of motion is called the dynamic equation of the manipulator. And then the vision is used for knowing where the object is and then reaching it. So for that, robotic vision is a sensor. Apart from vision sensor, there may be several other sensors attached to the robot for performing a work. And then the task planning. Once we know this information, the planning has to be made. That is the control, the control of the robot manipulator. The task planning may be, for example, we want to optimize energy of motion, or we want to optimize the time of reaching an object. So various planning has to be done. According to that plan, it has to be controlled. The robot should be controlled. So these are the main topics. Under this topic, the various studies are made. So next slide, please. So this shows a very simple two-dimensional robot, two-arm robot manipulator. As we said, it is moving only in a plane. Okay. And then three-joint robot manipulator, this one. So here, if you see that this is the first link, second link, and third link, and there are 3 degrees of freedom. The 3 degrees of freedom means 3 angles are required for controlling this one. Yeah, there is this thing, it's not visible. So here there is one actuator, the second actuator, and this is third actuator. So 3 rotations are required so that the end effector can reach a particular position. So we can see that for this particular position, there are several solutions. The link can be like this, or it can be like this also, or you can adjust this link in a suitable way, and so you can get infinitely many solutions for controlling this particular robot manipulator. See, given the position of the end effector, if you say there is a coordinate system, XY coordinate system on the plane, and the end of the manipulator coordinate is X comma Y, then what are the values of this theta 1, the angle of rotation? Here we call it as theta 1, this one as theta 2, and this one is theta 3. So given X comma Y, this position, what are the values of theta 1, theta 2, theta 3? That relation, we call it as the inverse kinematics. Direct kinematics is the position here. What is the relation between X, Y, and theta 1, theta 2 in this two-arm manipulator? Yeah, so next slide, please. Yeah, so directly we can see that if we have this X comma Y, the robot manipulator is with two arms here. So we first fix a coordinate frame. As we have seen, we need a world coordinate frame. That is the reference frame, we call it as XY, this one. Now, the origin is kept at this first joint, and XY are fixed arbitrarily. So we got a reference frame. Now we fix a coordinate frame at this joint. So that coordinate frame, we call it like this. We extend the first link, and that line we call it as the second x-axis, and the perpendicular line we call it as the y-axis at this joint. So by fixing in this particular manner, we have the coordinate frames at each joint here. Now we can easily see that the relation between this xy and theta 1 and theta 2. How we measure theta 1? From the x-axis to the first link, we call it as theta 1. And from the extension of the first link to the second link, we call it as theta 2. So from the base x-axis to the second link, the angle is theta 1 plus theta 2. So using this theta 1, theta 2 and xy, we can easily see that the next slide, the relation is very simple. X is L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Y is L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So this equation is called the direct kinematics equation for the two-link robot. Okay. So, yeah, next slide, please. Yeah. So if you see this first line, it is x equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y for this robot manipulator. Now, if a point is given, how do we calculate this theta 1 and theta 2? That is what we want, isn't it? For example, if the robot has to move to this particular position, then it has to rotate like this, isn't it? Some angle theta 1 should be rotated, and then theta 2 should be calculated so that it reaches this position. The same point can be obtained by another structure, that is, the first link can be like this, the second link can be in this way. So there are two different solutions for the inverse kinematics. Given x and y, find the theta 1 and theta 2 value. That is called the inverse kinematics problem. Direct kinematics means given theta 1 and theta 2, find x and y. That is a very simple one. Directly substitute theta 1 and theta 2 here, you will get x and y. The inverse kinematics is the practical problem. Given x and y, we have to find theta 1 and theta 2. So this is a very simple robot manipulator. There is nothing involved. With the usual manipulation, you can just square x and square y and then add these two. So this type of simple mathematical manipulation will give the theta 2 value as given in the last line. Theta 2 is cos inverse of this quantity. So given x, y and L1 and L2, we can easily calculate this theta 2, and in the next slide, the theta 1 also can be calculated. So these can be easily verified, nothing involved in this. So theta 1 is given in the last line in this slide. So this solution gives the inverse kinematics problem for the 2 degree of freedom manipulator. Now we come to the general robot manipulator. Let us say if you have a manipulator moving in space, which has say 3, 4, 5, 6 many degrees of freedom, a complicated robot manipulator. So then it is not possible to solve in this particular manner. As we have discussed for 2 degree of freedom, it is not possible. So now we need a more information about the 3-dimensional space and rotation matrix, translation matrix, etc. And then we formulate a homogeneous transformation like this. So first let us see what is a transformation, coordinate transformation. For that, if you see briefly, so anyone having any doubt also you can ask in between. If you want to ask something, you can ask. Okay, so I'll be happy to reply. If something is not clear also you can ask. Okay. So is it audible?
Yes, sir.
Hello? Yeah,
Yes,
okay.
sir. Audible, sir.
Okay. So we have the XYZ coordinate frame, that is the fixed coordinate frame, world frame. Then the coordinate frame is rotated and the new position is now x-axis has become u axis, y becomes v, and then z becomes w. So XYZ axis and UVW axis are given here. So what is the relation between these two axes? For doing that, all of you might have studied the rotation matrix formulation. So we will not go step by step here elaborately because these are all known topics. But if you have a doubt only, you can ask. Okay, so next slide, give a relation directly. So we can see that if P x, Py, Pz, it is a point in the XYZ space, and the same point is denoted by Pu, Pv, Pw in UVW space. Then what is the relation between this coordinate, UVW coordinate, and XYZ coordinate? It is given by this matrix, where Ix, Iy, Iz, these are called the axis of XYZ. X-axis, Y-axis, Z-axis, unit vectors, and IU, IV, IW are the XYZ coordinates of UVW space. Okay, unit vectors in the direction. So if you take dot product between these vectors, and it gives a rotation matrix directly. So for example, if we rotate about the axis, rotate about x-axis by an angle theta, then we will get this matrix, the rotation matrix. If you rotate about the y-axis by an angle theta, keeping x and z as a fixed position, that means x-axis is coinciding with u-axis, z-axis is coinciding with the w-axis, only y-axis is changing. Then we can see that the rotation matrix is given by this one by applying this one, because the x-axis and u-axis are coinciding. So this dot product will be 1, and here this 2 will be perpendicular, Therefore, this will be 0. 1, 0, 0 will be obtained. The first one. And only the remaining things will change. So this can be easily verified. The fundamental rotations will be given by these variables. This is called the general rotation. Okay. If all the coordinate axes are disturbed and we got a new coordinate frame, we can use this rotation matrix as a general one. Yeah, next slide. So it gives a simple example that if you are rotating about the z-axis by this much angle, 60 degrees, then what will be the relation between the x, y, z coordinates? If a point is given, 1, 3, 2 is given in the XYZ frame, then what is the corresponding value in the UVW frame? That can be calculated. So next slide, please. These are standard examples. You can see. That is 432. Yeah. So as in the last slide, we have seen the rotation matrix is a 3 by 3 matrix, and homogeneous transformation matrix, we make it as a 4 by 4 matrix. A rotation matrix can be written as a 4 by 4 matrix by keeping the 3 by 3 matrix in the first block, and then last row is 0, 0, 0, 1. Last column is also 0, 0, 0, 1. So then we call it as a homogeneous transformation representing a rotation. But if there is no rotation, only translation is there. The x, y, z coordinate is shifted. Only the origin is shifted to a new position as given. Let us say ABC is the new position of this thing, the origin. Then we can write it in terms of the homogeneous transformation. First 3 by 3 matrix is the identity because there is no rotation, and the translation origin is shifted to the position ABC in the last column. So it will be ABC, and then 1 is the last column. Last row is 0, 0, 0, 1. So a 4 by 4 matrix will indicate the translation alone. Similarly, if there is a rotation as well as translation together, then we can write a general homogeneous transformation matrix. Okay. Yeah, next slide. So when we consider the yeah, 1 minute, I'll share this thing. How to share a page, a new page. Turn on caption.
Sir, you would like to share your screen?
Yeah, one blank page. I want to write it on that. No.
Okay, I'll stop my representing the screen. Then you can start, sir. Please by presenting your screen.
Yeah. Okay. Yeah.
Yes, sir. There is an option present now.
Okay.
Yes, sir.
But again, you have to open this
Yeah,
same
again
thing.
yes, sir. Yes, sir. I'll again
Yeah.
start.
Why it is not coming? I don't know.
Sir, there is an option present
Yeah.
now.
Yeah, in present I have taken, but that particular is not opening. Share. Some blank page is there, that is not coming.
Have you started share your entire screen?
Entire screen.
Yes, sir. It would be better.
Yeah. In that there is no screen. Is it visible?
No, sir. Sir, go to the present now tab and then your entire screen. Click on the entire screen. Click on your entire screen. Then your screen will be visible to us.
Yeah. But in that particular file is not there. Blank file.
No, whenever you will open a blank file on your system, it will be visible to us. Whatever you will do with your system, then it will be visible to us.
Yeah, is it visible?
No, sir. So please go to the present now tab.
Now is it visible?
No, sir.
Present now.
Yes, sir. Click on the present now, then entire screen. Then it will be visible to us.
Yeah, present now. Is it visible? Blank slide.
Sir, actually, after clicking on the present now option, so there will be a window.
Yeah,
Yeah.
share.
Show your Google Meet screen. So you have to click on the screen, then you have to share it.
Yeah, it is showing your entire screen.
Yes, sir. So after you clicking on the entire screen option, so there will be a small window opening.
Yeah, in that window.
On that window, you have to click. So now currently it will show your Google Meet window. So you have to click on that window, and then the share option will be enabled. Then you have to click on the share.
Yes, sir.
Yeah, that I have clicked. Is it visible? This
No,
window.
sir. Actually, it will show us the your complete window. It will be showing to us. It will be visible to us.
Yeah, is it visible?
And now it is visible, sir.
Yes, sir. Now it is working.
Now you can open your presentation, so we can see your presentation now.
Yeah.
Yes, sir. Now this is the blank page, right?
Yeah, blank page. No? Yeah.
Yes, sir.
Okay.
Yeah.
So see, when we have a coordinate frame, X, Y, Z. The origin is there. Then if it is shifted to another position, different origin, and with respect to this, if it is ABC, and this new one is UVW, then the homogeneous transformation, it is the identity matrix 1 0 0 0 1 0 0 0 1 ABC 0 0 0 1. So this is the homogeneous transformation. And if the rotation is simply there, we have X, Y, Z and UVW, then the homogeneous transformation is the rotation matrix R 3 by 3, and then we have 0 0 0. So this 4 by 4 matrix is there, are the two things we have. So now if we are having a rotation, the X, Y, Z, if there are series of translations and rotations, let's say it is translated here and then it is rotated. So what we are doing it is, this is the fixed frame, and then next we have a moving frame, let us say M frame. And then from M, we have got M1 frame. First, the origin is shifted to this place here, and then there is a rotation about the new coordinate frame. From M frame, we got M1 frame. Then what is the relation between the F frame and M frame? So what we have seen is the relation between the F frame and the M1 frame. This is how we write here. If you are starting with the F frame, after making some rotations, we reached the M1 frame, then we will write it as FTM in this notation. So that is obtained by, first we have got F frame and then we got M frame. FTM is the relation between F and M. And then M is rotated and then we got M1 frame. So that is multiplied by MT M1. So this is the relation. In general, if you take FT some M2, for example, after M1 again you got some other M2 by making some rotation or translation, then we should multiply all this. FTM1 is the relation, FTM is the relation between F and M, and then multiplied by MT M1, and then M1 is disturbed and we got M2 frame. Okay, so this three product will give the relation between the base frame M, F frame, and then the last frame. Let us say after some time we got M2 frame like this. So what the relation between F and M2 frame is product of all these things. So this is one way of finding the relation between one frame to the another frame. Here we have to note that we are making the rotation or translation with respect to the current frame. That means from F we got M. M is now called the current frame. Then this current frame is disturbed and we got M1 frame. That M1 frame now is called the current frame. With respect to M1, we are making translation or rotation. We got M2 frame. So that is how we use the terminology, that the translation and rotation with respect to the current frame. If it is done, then we have to multiply one by one in this way, in the right side. But other situation is if you are rotating with respect to the base frame all the time. First we have the base frame, the F frame, and from F frame we make some rotation, let's say about its axis, and we got the new frame. This is the M frame. With respect to Z means Z will not be disturbed, only X and Y are disturbed. and we got, let's say, x1, x2, x1, y1, z1. And now, if we again rotate or translate this M frame with respect to the base frame. For example, if we make a translation of the M frame with respect to the x-axis of the F frame, then it will become like this. Okay. The z-axis will be parallel here, and y1 axis will be like this, and x1 axis will be like this. So if you are making a translation with respect to the x-axis of the base frame, then we have to multiply in the left hand side. Okay. So first we have got FTM. Now M is disturbed by a translation, that is identity and EA00. As I said, the translation is along the x direction of the X frame. So we have got like this. And further, if M frame is disturbed with respect to the F frame itself, if we make a rotation about the Z axis of the F frame, then we have to multiply the rotation in the left side. So these two type of, from the starting transformation, we call it as T1. If we keep on making changes with respect to the current frame, we have to multiply in the right hand side. But from the starting transformation, if we keep changing with respect to the base frame itself, all the translation rotation, we have to multiply in the left side. So that will give the relation between the starting frame and the last frame, some MK or something. After K steps, we will get this, either this relation or we will get this relation. Okay. So it depends on how we are doing the translation and rotation with respect to the current frame or with respect to the base frame. Yeah, now you can show the video, okay, slides. Yeah, can you show this thing, slides? So now I will just close it. Okay. Yeah. So these are the two type of things. We have to, the transformation, the rotation and translation with respect to the base frame, XYZ frame, then using the pre-multiplication. And if you are doing with respect to the current frame, every time we get a new frame, and with respect to that frame we are rotating or translating, we have to post multiply. So that is how we get a relation. Yes, next slide, please. Okay, so these are some example, but we can go quickly from now to various other topics, that is the kinematics of the robot manipulator. So using this particular homogeneous transformation, we have to find the relation between the base of the robot manipulator and the end effector of the robot manipulator. That is called the DH algorithm. This one, this particular thing, we call it as the DH algorithm. Yeah. So the DH algorithm also, I will not go through very rigorously because it is itself is a very, again, a topic of 1 or 2 lectures. So here at every, as we have already seen, there is a world coordinate frame. That is a frame attached at the base of the robot manipulator. At every joint, we have to fix one coordinate frame. That is called the joint coordinate frame. So this DH algorithm gives how to fix the joint coordinate frames. So first we have to fix the Z-axis at each joint. Then we have to fix the X-axis using the Z-axis, and then Y-axis can be fixed. Then we got coordinate frames at each joint. If you follow this particular procedure, finally we will get a 4 by 4 matrix. Yeah, next slide, please. So yeah, here we have the base of the system. If you run it, it will show this thing. It will fix the coordinate frame at each joint. So the second joint is prismatic, third joint is prismatic, fourth is a revolute joint. Now, according to the DH algorithm, it will fix the first, the z-axis is fixed, the vertical upward direction, because it is rotation. Here also vertical upward rotation, and then this direction is the prismatic direction. The red line vertical is the prismatic direction for the second joint. So these are all the z coordinate fixed. Then according to DH algorithm, x-axis is fixed and then z-axis. So we got a coordinate frame at the base and a coordinate frame at the end effector. Once we know the relation between the base and the end effector coordinate frames, then we can control it in any manner we want. Wherever we want to reach, that can be done. Okay, so next slide, please. So that is what the matrix given in the last line, the 4 by 4 matrix, it gives the relation between the ith coordinate joint frame and the I minus coordinate frame. I minus 1 to I coordinate frame. What is the relation? By using the homogeneous transformation is given by this particular expression, using the parameters of the robot manipulator as described in this slide. Okay. So these are all various other technical things, but main thing which we need is there is a relation between the ith coordinate frame and the I minus 1 coordinate frame. Yeah. So here we can see that there are 6 joints and there is a base coordinate frame and the end effector coordinate frame. How to? For each joint, the parameters are defined here. Theta is the joint angle, alpha is the joint twist angle, and A is the joint distance, and D is the joint distance, and A is the link length. So all these are to be calculated according to the structure of the robot manipulator as given in the DH algorithm. Once we form this table using the matrix given in the previous slide, we can write the relation between first and second, that the coordinate frame of the base and the first joint. And then 2 and 3, the second and third coordinate frame can be written. The relation is written by using the previous slide. If you put I is equal to 1, 2, 3, etc., we will get 0, T1, 1, T2, all the relation between the coordinate. Now multiplying all this, we will get 0, T6. That is the 0 means the base coordinate frame, 6 is the end effector coordinate frame. The relation between the coordinate frame at base and the coordinate frame at end effector is given by 0, T6. That is the product of all these coordinate frames. Okay. So next slide, please. So here we can see that 0T1 is the relation between the base frame and the first frame. 1, 2 means first frame and the second frame coordinate systems, etc. The product of all this finally will give 0 frame and the 6th frame coordinate systems, the relation. So this is a very useful relation. Once we know the product, all these entries are known. So this gives the relation between, if a point is given with respect to the base coordinate frame, the same point we can calculate with respect to the end effector coordinate frame, the 6th coordinate frame. So what is the end effector coordinate frame? It is the hand of the robot manipulator, the gripper or the tool position. So once we know this 0T6 relation, it gives the, if an object is placed in the world frame, then we will easily know that where that object is with respect to the hand frame, the end effector frame, by this particular matrix. So this is called the arm matrix of the robot manipulator. It is a very important matrix. For every different robot, arm matrix will be different depending on the structure. So that can be calculated by this one. So once we know the position and orientation of the end effector, we can easily solve this problem. There are 12 equations for every given position and orientation of the end effector. What are the θ1, θ2, etc. of the joint angles that can be calculated by solving this 12 equation, nonlinear equation. This will give many solutions. For the same orientation, we can get several different solutions, θ1, θ2, etc. that can be solved by the inverse kinematics problem. Because in the practical situation, we want to take an object, we can take it using different positions of our hand. Maybe the end position is the same, but all the position of the arm and the angles which we rotate our arm, etc., that may be different. There may be many solutions for the same position and orientation. So we will get from this set of equations, and accordingly the control can be calculated. Okay, so next one is okay. So example of inverse kinematics. So this is not required. It is a given position and orientation, how to solve those 12 equations mathematically, that can be easily solved by observation or by simple manipulations of mathematics, etc. that can be solved, or by using MATLAB, etc. can be solved. Okay, yeah. So the trajectory planning. Now, once we know the position and orientation of the object, the next aim is to reach that object from the current position of the hand. So we have to plan a trajectory between the current position and the end position. So the point-to-point motion is there, or continuous path motion. We can plan how the end effector should move continuously to reach the point. That is one thing. Or give the initial point and the final point, then we can find the intermediate points. That is another way of, see, in some problem, initial and final points are very important. Intermediate points may not be very important. But in some problems, intermediate problems, positions are also very important, because there may be obstacles in between. So to avoid the obstacle, you should also know how it should travel in between the initial and final position. So continuous path motion training is required for such situation. And if there is no obstacle in between the initial and final position, we can just train it for point to point. And intermediate path can be anything we can select. The next one. So here we have a 3 degree of freedom robot manipulator, which draws a circle. So the angles, there are 3 angles are to be controlled for doing this particular motion. Okay. This is done by, first we have to write the DH algorithm for this type of robot manipulators, and then the position and orientation of the end effector are to be given, because this robot has to move along a straight line from one point to another. So we have to give in which way it has to move, or using a vision sensor, it will calculate what are the points on which the end effector should move. Accordingly, the angles will be adjusted using the inverse kinematic solution of the problem. Yeah, next one. So this is like a point-to-point structure. This is the initial position and that is the final position. It has to reach that particular hole and make a screw. So intermediate points are not very important. There may be several points, several intermediate paths available. So it can plan a path accordingly. Here, another thing which is important is how much force it should apply on the screw so that it goes inside and it rotates the screw, etc. So that will be considered later. That is on the dynamics part. But kinematics part is only the initial position and final position and the intermediate path, how to calculate and how to adjust these angles. So these relations are called the kinematics relation that can be seen, that we have seen in the previous thing. Okay. So how to plan a trajectory given a initial point and the final point, how we should travel in between. So for that, the standard technique of planning a polynomial trajectory is given. So if we are given the initial position, we know theta of 0 and theta of final position. Okay, 1 degree of freedom. And also we know the velocity, initial velocity, how much it should be, final velocity, theta dot. Then, so using these 4 values, initial position 2 values and final initial velocity and final velocity 2. There are totally 4 data is given. Using that, how to calculate the intermediate angles. So that can be done by planning a 4-degree polynomial here. So we are writing a alpha 0 plus alpha 1t, etc. There are 4 constants which we have to decide. So that can be easily done by substituting the 4 values at t equal to 0. We will get 2 equations. At t equal to f, we will get 2 equations. So there are 4 equations we will get with 4 unknowns. Then these 4 unknowns can be calculated uniquely. And that will give the angle theta for all the values of t. Intermediate time value, we can calculate the angle theta. So this is for one variable, single joint. But the same technique is applied for any type of robot. Even if it has 6 degrees of freedom, theta 1, theta 2, up to theta 6. Then, and if we know the initial position and the initial velocity of the joint, all the joints and final position and final velocity, we can design 6 different such polynomials, because for each angle we have to design one polynomial. So 6 different polynomials can be designed and we can calculate the coefficients for each one of them. That will give the position and orientation of the intermediate points. Okay. Yeah. So next slide, please. So this gives the calculation of this. As we have seen, theta is given by the 3-degree polynomial, and we substitute theta of 0 equal to a0 and theta dot of 0 is a1. This a0 and alpha 0, alpha 1 are calculated. Similarly, when we substitute the final time, we can get 2 equations, and then, so it is a simple system of 4 algebraic equation matrix. Using the matrix method, we can solve the equation. So next slide. So this is the procedure. This vector, the left-hand side vector gives the 3 information at the time t equal to 0, and the last 3 gives the 3 information, position, velocity, acceleration at the final time. So if you are given 6 information, we need a 5-degree polynomial with 6 coefficients. alpha 0, alpha 1 up to alpha 5. In the previous one, we got four data, initial position velocity and final position final velocity. We can fix a 3-degree polynomial. Now we got 3 information at initial time and 3 information at final time. For that, we can fix a 5-degree polynomial, and then we can find the coefficients accordingly. So, but if you have, say, n information like this, you can fix a n minus 1 degree polynomial or more degree also. We will get many solutions in that case. Okay. Yeah. Yeah. So this particular problem, it gives a familiar, many videos are available for such problems. So a bottle is thrown from one position and the robot has to catch this one. So it has to adjust its position and orientation according to the final reaching position of the bottle. So it has to calculate using various sensors, vision sensor and velocity, acceleration sensors, etc. From the initial position of the bottle, which is thrown, to the final position, it has to calculate and then adjust its end effector position to catch that object. So it is a trajectory planning problem and a high level problem. It has to be done online. So it may not be so simple, but it is, the main problem is the trajectory planning and the using the dynamic equation, the torque, etc. should be calculated properly. So that we will see in the next, using the dynamics. See, when we see a robot manipulator in motion, not only the kinematics is important, the dynamics is a most important thing, because dynamics involves the force or the torque acting on the body. So here, the robot arm dynamics is the equation of motion of the robot as given, explained here in this particular slide. The way in which the robot manipulator motion arises using the force and torque is called the robot dynamics. Okay, so we have two approaches. Next slide. For writing a dynamic equation, we have two different approaches. And so here it shows the two things. Yeah, next slide, please. So here there are two approaches. The Newton's approach, that is mass into acceleration equal to force or the torque relation, or the Euler-Lagrange approach. These are the two equations which, two approaches we can use to derive the dynamic equation of the robot manipulator. And using the dynamic equation, we can control the robots. So first, how to write a dynamic equation, that is what we will see briefly in the next slide. So the Euler-Lagrange formulation is as follows. Every rigid body has a kinetic energy and the potential energy. So the Lagrangian L is defined as K minus P, kinetic minus potential energy of the body. And the first equation, d by dt of del L by del Qi dot minus del L by del Qi equal to tau suffix I. So this equation is the set of equations. I is equal to 1, 2, 3 up to n. If there is a n degree of freedom manipulator, n arm robot manipulator is there, then there are Q1, Q2, Qn. These are the joint parameters. We have seen the angles of rotation, etc. So with respect to this Qi, we write this equation, we calculate the kinetic and potential energy and calculate the Lagrangian. So that will be function of all this Qi, Qi dot and Qi double dot, etc. So when we calculate this d by dt of del L by del Qi dot minus del L by del Qi equal to 2i, this gives the equation of motion of a robot manipulator where I is equal to 1 to up to n. The n is the number of joints. So if there is a n degree of freedom manipulator, there will be n such equations. The system of equation, they are all second order differential equations. So first we see here the simplest model, 1 degree of freedom manipulator, which is the simple pendulum. Here, pendulum of length L with a mass m attached at the end. It has a kinetic energy and potential energy as described in this slide, and L is calculated like this, K minus P. So this gives the outline of how to calculate. Okay. So this later one can study leisurely, but here I'm just giving a brief outline of how to derive these equations. So kinetic energy is given, potential energy is given, and we have the Euler-Lagrangian equation in the last line. So the equation of motion of the simple pendulum is given in this page. Okay. The next one we have, next slide, we have the 2 degree of freedom manipulator. Earlier we have seen how to write the kinematic equation, the relation between the end effector and the joint angles. Now we can see how to write the dynamic equation of this. So for this purpose, we should write the kinetic and potential energy of this manipulator. So each joint has separate motion. Okay, independently they are moving and they have a kinetic and potential energy. And so the length, mass, everything will come into picture here. So in the next slide, it shows a, because these steps are also again involved, we have the Ki, the kinetic energy is given in this particular step. In the first one, it is given Pi, the potential energy of the link. So by using the first step, that is half times Mi, the V transpose into V, the velocity transpose into velocity, that is like half mv square. And for the revolute joints, we use the omega transpose I omega. Okay. So the kinetic and potential energy as described here are calculated, and the equation of motion, the next slide please. So the previous details can be seen, but the final result is like this. The tau1 and tau2, the torque to be applied at each joint is given by the tau1, tau2 left side, and the matrix expression given here is the inertia matrix. The first matrix, 2 by 2 matrix, is called the inertia matrix, and here theta1 double dot, theta2 double dot is given as in the right hand side as the first vector, first term, and in the second term theta dot and theta are involved, theta1 and theta2, theta1 dot, theta2 dot are involved. In the third term, the g term is involved, the gravity term is involved. So these 3 terms are very important in the dynamic equation. Once we formulate the Euler-Lagrange method, finally we will arrive at the equation in the standard format like this. The next page we can see the standard way of writing the dynamic equation of any robot manipulator. So if it is here, it is a 2 by 2 manipulator. So The first matrix M is called the inertia matrix. The second one is the centrifugal and Coriolis force vector. The third one, G, is called the gravity vector. And the right hand side, tau, is the torque vector, torque or force. So the right hand side, tau, means it contains tau 1, tau 2 up to tau n. There are n variables. So they can be either a force if it is prismatic joint or torque if it is a revolute joint. So we get a vector if it is a n-dimensional robot, n-arm robot manipulator. The right hand side is a vector belonging to Rn, and it is a function of time. As time changes, the force and torque also keeps on changing. So time varying vector is there in the right hand side. So that is the important term because it is the controlling term. Only when we apply a force or torque on a robot manipulator, the robot can move in a proper manner. So our aim mainly is, this is the control system, we can say. The equation, the dynamic equation which is given in the first line, it is a general equation for any type of robot manipulator. And the right hand side is the control of the robot manipulator. We have to identify this control suitably so that the particular job is done. Whatever job is assigned to that robot manipulator, how to perform it is in the vector tau. How to control is the main aim of this one. So, okay. So for two-arm manipulator, these terms are written in this particular page. M is the inertia vector, C is the Coriolis force vector, and this G is the gravity term is given here. Okay. Yeah. So the next slide. So we have to plan the control here. The position control or the force control, hybrid control means both position and force control of the robot manipulator. And different types of control can be applied. Robust control or adaptive control, neural network based control, etc. And nowadays, a lot of evolutionary algorithms have come up for like fuzzy or genetic algorithms, etc. Many types of controls have come for controlling various systems, and robot manipulator is a particular system. So various techniques can be applied for controlling. And the PID, PD controls are the standard controls which you might have all studied in different courses. Okay. So next page, please. Yeah. I think these are all some standard videos which picks and plays some objects. These can be skipped. This is also a heavy car is lifted by two robot manipulators, coordinating robot manipulators. So all these problems, even though they are very practically important problems, the technique involved is using the path planning, the control planning, etc. The torque, how much torque to be applied to lift a heavy weight, that is very important, that calculation. And then the position and orientation of the end effector, how to, for example, this is placing a wheel at a particular place, position and orientation. So the computation of those position and orientation accurately is very important for performing this type of things. So the technique is, the basic techniques are kinematics and dynamics of robot manipulators to be studied, and then the accuracy, etc. will be done by various current technology, that is like neural networks and various other algorithm techniques can be applied for learning and then more intelligent way of controlling it. Okay, so next slide, please. Yes, so here we will see a very basic way of controlling. This is the first step, you can say, and these steps can be improved for more sophisticated control problems. So take any robot manipulator, it will have a dynamic equation as given in the first line. M Q double dot plus C plus G term equal to torque term. So the torque is the important thing which we need to calculate to perform a particular job. So what is the particular work which is given to the robot manipulator? That is the Q desired. The Q here means Q1, Q2, Qn. The joint angles at each joint is indicated by Qi. And Q desired is as a function of time, how those angles to be adjusted is already given to us, because we know a particular path in which the robot should travel, the end effector should travel. For traveling in that path, it has to solve the inverse kinematics problem. So all this Qi value, Qi means all the theta values, the angles are calculated. That is the desired trajectory, we will call the desired joint trajectory. Now, how actually it should perform? This Q of t here indicates the current position. The end effector may not be in the desired position in the beginning. It may be in a different position. So it has to reach the desired position as time changes. So the error in the desired QD and Q of t, QD of t minus Q of t, it gives the error at each instant of time, which need to be minimized. We want to make that error tending to 0 as quickly as possible so that the robot travels in the desired trajectory continuously as time changes. So E of t is the variable which we want to make 0. E of t should converge to 0 as t progresses. For that, you can plan a torque like this. The torque tau of t given in the equation 2. First, how it is selected, tau of t is selected as C, because we know all the terms in the first equation, equation 1. M q q dot is known to us because the equation of motion is given. C q q dot etc. These expressions are known to us. Now, what is q? Q is the current position. Q dot is the current velocity of the robot. So when a robot is moving, the current position and current velocity is known by the sensors. The sensor will calculate the current position and the current velocity. So q dot is known to us, and that can be substituted to calculate C of q dot and G of q. So the equation 2 gives tau of t is C q dot plus G of q. These two things are known to us, plus some unknown term, we take tau dashed. Okay, this has to be calculated so that the error E of t tending to 0. That is our aim. What is tau dashed? That is also given in the last line here in the equation 3. It is selected, see E of t is also known to us because we know the current position qt and we also know qd of t. The desired position is also known to us. So the difference between that is error, and its derivative will give E dot. So using this E and E dot, equation 3 is written. So by substituting all this in the first equation, we can easily obtain the next slide. We obtain the equation, the second order differential equation in terms of E. E double dot plus K1 E dot plus K2 E equal to 0 is obtained. Now it is easy to find this K1 and K2 because it is a very simple second order ordinary differential equation. Its solution is given in the equation 5 here. Some constant into e to the power the lambda 1t plus constant into e power lambda 2t, where lambda 1, lambda 2 are the solution of the auxiliary equation. It is an ordinary differential equation which can be solved. So if this lambda 1, lambda 2 both are negative, then obviously this error will tend to 0 as t goes to larger value. Okay, so if lambda 1, lambda 2 are very large negative numbers, it will reach 0 very quickly, as close to 0 very quickly. So we have to select this K1 and K2, the coefficient of the auxiliary equation, the second degree quadratic equation, in such a way that this lambda 1, lambda 2 roots of the polynomial are negative numbers. So once we select K1 and K2, then it is very easy from the previous slide to calculate the torque, and that particular torque will take the end effector in the desired path. So this is the simple procedure for controlling the robot manipulator, isn't it? We can call it as the PD control. Proportionate and the derivative terms are used. E and E dot is used in this calculation. So it is called the PD control for controlling the robot manipulator. Okay. So next slide. Yeah. So here I'll go quickly. This is on a biped robot manipulator, a walking humanoid type of robot manipulator. So there is a lot of difference between a simple robot manipulator, as we have seen in the previous slides, and the humanoid robot manipulator, because here it has, even though it has links and joints, as in the case of manipulator only, but it has two end effectors. 2 feet are there, and sometimes both the feet will be on the ground, and sometimes 1 feet will be on the ground. So when single feet is on the ground and another feet is moving in the air, that will act like a robot manipulator, because there is a fixed position and a end effector position which is moving freely. So that is like a simple robot manipulator. But when both the legs are on the ground, then it is like a parallel robot manipulator, and only the other joints has to move. So two things are combined here, and we have to control this robot for moving from one place to another place. It is not like the previous example, like manipulator, for which the base is fixed always in one place and the end effector only is moving. But here it is the base will be base for one moment, and after some time that will become the end effector. The end effector of the previous step will become the base of the current one. So it will be keep on changing its role. And the kinematics and dynamics equation can be derived for biped robots also in the similar manner, because it has same type of links and joints. But only thing is, as the steps changes, the role of the equations will keep on changing, and how to apply the torque, etc. Most of the things are common to the robot manipulator and the biped robots in the similar manner. Okay. Yeah. So next slide. So here there are two phases as I described, the single support phase in which one foot is on the ground, another is moving on the air. Double support is both the legs are on the ground. So here we will describe the simple thing. T0 to T2, one particular step is taken. The time starts at T0 and ends at TF. That means the foot starts from T0 and then end at TF and it lands on the ground. So at that moment, the other foot will start moving upwards and then go towards the ground of for the next step, second step. So T0 to TF is single step and it is divided by two phases, the single support phase and double support phase. So T0 to T2 is double support and T2 to TF is the single support phase. And how the walking can be planned is the thing which we can see quickly here. Okay. Yeah, you can, if it is running, you can see this. So here we see the single support and double support phase while the robot is walking. The next one. So here there are several joints. One is the hip. There are two hips for the robot manipulator, left side hip and the right side hip. The leg length is L1 plus L2. Hip to knee and knee to the ankle is one. There are two link, and then the foot is having from the end of the knee to toe. The sole E to S, S to T has sole and toe of the robot the foot. So there are four links in one side, four link in the another side. The joint of the two hips, that is another link. So there are four in one side, four. So there are 8 and 9 links are available for the simple planning of a walking robot. Okay. And apart from that, there is an upper body for this robot, and how it should be made walking in a stable manner. That is the main question here. So when we lift the single leg and keep one leg on the ground, there is no guarantee that it will be moving without falling. So there is a question of stability also coming along with the trajectory planning. In the previous robot manipulator thing, there is no question of stability because one side is always fixed on the ground. So it will not fall down. But in the walking robot, there is a question of falling down because it has a mass at each link. And when we lift one leg, then it may fall down. That we experience in our walking also. If you are not balancing properly, we will fall down. So how to balance the robot manipulator while walking properly is the main question of stability. So while planning the trajectory side by side, the stability is also to be analyzed. That is an important thing. So here two phases are there, double support phase. Both the foot are on the ground, and from the one foot is lifting the foot from T0 to T2. That much time it takes for lifting the foot from the ground. After that, it moves in the parabolic type of path from T2 to TF to the final time. So how to plan this parabolic type of path is the question. after planning that, is it stable also? Because when the foot is moving along this path, the other links also should adjust themselves so that the balance is made. So how to do? The hip should simultaneously move forward. Okay, from the time T0 to TF. So all this should be done simultaneously so that the robot keeps on walking properly. Okay, so next slide. So for this, we indicate here the swing legs joint trajectory. For this, we have to give initial position, initial velocity, and final position, final velocity. We know the length of 1 foot, how far the foot can travel in 1 foot, one particular step. So we can give the step length and the velocity with which it should land when it reaches the ground, and the velocity with which it should start in the beginning time. All this will be given. There are here 4 constraints given. Accordingly, we can plan a polynomial trajectory. As we have already described, if we are having 4 data, initial position velocity, final position velocity, and then we can plan the polynomial trajectory, and then it can be easily obtained. The coefficient of the polynomial is obtained. We can plan this. The foot can walk along the particular polynomial trajectory. Okay. Yeah, next slide. And stable leg also should have a trajectory. This one. For that, the hip should move forward. XH means the x-axis of the hip position at T0, the initial time, and XHTF is the position of the hip, X value coordinate of the hip at the final time, and initial velocity and final velocity. These are all indicated. So how the hip should move also can be planned by this trajectory. So this trajectory planning are very routine thing in the simplest problem. Even though in practical situation it may not be so simple, it is only indication of we can plan some trajectory. That is the indication here. Okay. Yeah. Next slide. So this shows that after planning such trajectory, how the simulation shows the various positions of the leg at various instances of time. It moves like this. The next one. And this shows the stable leg. That is, the leg is on the ground. Initially, the foot, when it is landing, it is in the slanting position. The foot is in the slanting position, and slowly it comes down and then finally coincide with the ground itself. So from the first position, which is slanting, and the last position, which is on the ground, the foot is shown in the blue color. By the same time, how the leg is changing its position from the beginning to the end is shown in the V-shaped red color. Yeah, next slide, please. So now the zero moment point is the very important concept in the biped robot manipulator. For the humanoid robot, the calculation of ZMP, that is the zero moment point, is very important. See, if an object is not moving, the center of mass is very important. For an object which is stable, stationary, and it should not fall down. What is the criteria? The center of mass should fall within the object. If you make a projection on the ground of an object, we will get a shape. So within that shape, the center of mass should be projected. Then it is guaranteed that the object will be stable. It will not fall down. But when an object is moving, the center of mass is not very important. The Z0 moment point, this is an equivalent concept. The zero moment point, which is calculated here, x z mp, y z mp. These are the xy coordinates of the zero moment point. It should fall in the region of the projection of the body. As the body is moving, you project it on the plane of motion. The ZMP coordinate should lie within that region. Then we say that it is stable. It will not fall down while moving. So if the object is not moving, then this you can say that xi double dot, they are all 0. Then the equation x and y will coincide with the center of mass coordinate. Okay. So this is more general concept for stability of a object which is moving. So this point should lie within the region of the projection as and when the body is moving. So while planning a trajectory, whether it is polynomial trajectory or any type of trajectory, when the robot is moving, we have to all simultaneously calculate this x and y ZMP point. It should also lie within the region. Then we can guarantee the stability of this thing. Okay. Yeah, next slide, please. Yes. See, these rectangles show the planning of the foot, where the foot should be kept. And the curved path, it shows the ZMP directions, how the ZMP will keep on moving as the robot takes its foot from one place to another place. The ZMP also should travel in the curved path so that the robot will not fall down. So that calculation should be maintained for the stability of the system. Why that curved path is coming? Because it always falls inside the region of projection of this body completely. See, if one foot is on the ground, then the ZMP should fall with, yeah, next slide, please. Yeah. See, here the rectangle shows the position of the feet. So the left feet is here, and the ZMP is starting from here, and then when single foot is on the ground, another foot is on the air, then ZMP should be within the foot area. Okay. And when the other foot is about to touch the ground for the next step, ZMP can travel from that foot area towards the next foot area, which will come to the ground. So it will travel in a zigzag path. The ZMP coordinate will travel in the zigzag path. Sometimes it will be under the single foot which is on the ground, and then sometimes it will be under the other foot which is on the ground. So it has to keep on changing its position. So we get a path like a sine curve or cos curve we are seeing here for a stable motion of the robot manipulator. Yeah, next slide, please. So this shows various simulation result. Okay, we have taken the length of the robot leg from knee to ankle, from hip to knee, etc. We have assumed some realistic situation like a human being height, and the foot length also we have taken 14-inch type of thing, and calculated the ZMP mass also to be assumed for this robot manipulator, as we have shown in the table. For this, the simulation is calculated, how the robot manipulator walks, Uh, so this picture shows the coordinate of the ZMP. The blue color shows the coordinate of the ZMP and how it travels for different. The second 2.1 second indicates that from one step to the other step it take 2.1 second. It is a slow walking actually. Yeah, next slide please. And this table shows for which situation we get a stable walking. For example, here, if you take the cubic trajectory in case 1, as described earlier, if you take cubic trajectory and one step is 2.5 seconds, then we get the initial hip velocity is given by VH. For this hip velocity, we get a stable walking. And for other cases, mostly we get unstable walking. And the bright, the bold, stable, it shows that the better situation. The step length, the time is 2.1 second. Okay, from single support to double support, the intermediate T0 to TF, if it is 2.1 second and the hip velocity is as given here, then we get a better stability curve as shown in the next slide. Okay. Yeah, maybe next slide you can show. This is not required, I think, all this. Yeah, so this shows the complete simulation result along with the upper body motion. And for the case 2.1 second foot, the step time and the hip velocity as mentioned in the table. So this gives a better stable walking of the robot manipulator as indicated. But one can, using trial and error method, one can identify various types of walking pattern and stability of motion of the robot manipulators. Yeah. This also you can skip. Next slide you can show. And this shows the simulation on walking on an obstacle, avoiding an obstacle. A small obstacle is kept in front and then how it crosses this thing. Yeah, next slide please. Yeah, no need. You can skip this slide. These are all standard. Okay. Yeah, next slide. So this lecture, it was just aimed to show various basic ideas of controlling a robot manipulator or a biped robot. And the dynamic equation of a biped robot is more complicated, even though procedure is same. The Euler-Lagrange formulation can be done. And so here we have, for robot manipulator, even dynamic equation is shown. But for biped robot, it is a much complicated thing. So you can refer to various papers on this topic for further research. If you are doing work on robot manipulators, you can refer to various books which are shown here as the basics in the reference. So thank you for this present opportunity to give this presentation. And if you have any question, you can ask me now.
Thank you so much, sir, for such an informative session, and you have given a deep explanation about the robotic manipulators and dynamics. Now the session is open for questions. Participants, if you have any doubts, you can ask Professor.
Sir, hello.
Yeah, yes, yeah.
Sir, my question is very basic. So, is there any particular type of motor which is used? First question. And suppose there are two arms, so how many motors will be required for that? Yeah, three arms are there. Then how many motors will be required?
Yeah, I'll just open the camera 1 minute. Yeah, actually, if as we have seen in the very beginning, the two arm manipulator, for example, here in this picture, there are four joints. One is the base, it is a rotation joint. You are seeing this particular thing, this picture.
Yes, sir, visible.
Here, the base is one motor, and another is a prismatic joint. It has to lift it upwards and downwards. That is another motor actuator. The third one is it has to move forward and backward. So there should be another motor which is making it moving forward, backward, and fourth motor. So in this particular picture, there are, say, four motors are required. And if you have, say, two arm manipulator, there should be two rotational motion. Yes. Is that your question?
Yes, sir, yes, sir. Which type of motors, basically, that was another question, sir.
Yeah, that depends on the requirement, which is the, for example, this Kara manipulator, as shown in one of the pictures, it will only move vertically upwards and downwards. It will just take an object and then it is only for moving. Can you show one of the pictures in the beginning? Maybe after 3-4 slides. The next slide, next to next.
So this one. Hello?
Yeah, I'm not seeing, no, I'm not able to see this thing, slides.
Oh, my slide is not visible too.
Yeah,
So slides are visible now, sir.
now it is visible, but small size. Can you make it
Okay,
full screen?
okay. Full screen I can, yes.
Yeah. So maybe previous slide. Yeah, here you can see that these robots are completely revolute joint. All of them are rotational joint. For this will be useful if there are, say, 6 rotations. 6 degree. There are something called Puma manipulators or the SCARA robot manipulator or several types of robot manipulators. So it for pick and place, if it is required, then 6 degree of freedom manipulator is required. Okay.
Okay, sir.
Any previous one? First, I have shown SCARA manipulator. Previous slide, can you show? Here, yeah, this one. The next one. Yes. So this is called the SCARA robot manipulator, not this one. The next one.
Sir.
No, you have shown a picture, no, just now. This one, yeah. See here, you can see that this robot manipulator can just go down and up. Only this is the purpose of this SCARA manipulator. it can rotate at the end effector, and it can lift the object up and then keep it down, or a screw type of thing. It can take a screwdriver and then rotate at that vertical position only. So the purpose is only this much. For that, there is a rotation here, and there is a rotation here, and it will go up and down here. So when the object is kept in any place surrounding, then it can go to that particular place and then take it up and down. Only for that purpose, it is Kara manipulator. Other manipulator, for example, this one, it has to take, it is not only going just up and down in the vertical direction, it has to take the object in different position, like catching a ball. When it is thrown towards it, it requires several degrees of freedom, like our hand. For example, our hand itself is having 7 degrees of freedom. If you measure how many rotations are there at various joints, you can see 7 degrees, excluding fingers, there are 7 degrees of freedom available. So according to the requirement, the joints can be added to a robot manipulator. Okay. Yeah.
Thank you very much. Thank you. So nice.
Any other question?
Any other questions from the participants?
Sir, I have one question. Sir, what about the controllability and stabilizability in terms of, big robot?
Controllability, as we have seen, the workspace, the beginning we have seen, there is, for every robot manipulator, there is a workspace. Okay. So if the object is away from that workspace, then we cannot control. We cannot reach that object. So the controllability itself is not there. But if the object is within the workspace, still the robot may not be able to reach, because the orientation may be a problem. Okay. So the workspace includes not only position, as well as it includes the orientation also. So if any object is within the proper workspace, the controllability is guaranteed. Okay.
Okay.
Because see, for example, if an object is in a very difficult position, even our hand cannot reach. See, we cannot bend our hand in particular position. We cannot even touch our back, isn't it? For example, some particular position of our back, it cannot be touched. So those type of positions are called singular position of a robot manipulator. So we have to avoid, so unless a object is in that particular singular position, always it is controllable. So we need not check the controllability as we do it in the control theory. Control theory is different. We write a control system and we design. Here, because it is a practical problem in a finite dimensional space, so controllability is most of the time guaranteed for a robot manipulator, unless the object is in the singular position. Okay.
And sir, what about the stabilizability? Because it might be possible that your system is controllable, as you have seen in that case. But
yeah.
It might be possible that we need to check about the stabilizability also.
Stabilizability comes into picture only when there is a control, isn't it?
Yes, sir.
So the control, what is stable, as we described, the error should be tending to 0. E of t is calculated. There is a desired task and the current position of the robot manipulator. The difference between that is called the error. The error should be stabilized to 0. For making that error tending to 0, you have to calculate a proper control. So when we apply various techniques like PD, PID, or any other current day techniques of evolutionary systems and all that, so we have to, our aim is only to make the E of t tending to 0 in all the cases. So as long as we design a trajectory, it is called stabilizable. The control which drives the error tending to zero is called a stabilizing control. Okay.
Thank you, sir. Any question
Yeah.
from any participants? Uh, I think there is no question. Yes, Dr. Satya, I think we can conclude.
Yes, sir. If there is any questions, we can wind up our session now. Thank you so much, sir. Thank you for sharing your valuable time and sharing your knowledge and very deeply about robot dynamics. Thank you so much, sir.
Yeah, thank you for this opportunity. And I think it is a very huge topic. The robotic itself is a course for one semester.
Yes, sir.
I try to give it very briefly,
E-
as
Uh,
brief as possible. So, okay. So
yes,
thank
sir.
you.
It was completely in detailed manner. Yeah.
Okay. Thanks a lot.
Thank you, sir. Thank you so
Thank you, sir.
much.
Thank you so much.
So
All
I
the
will give now.
participants. Yes, sir. All the participants are requested to please fill the feedback form. Link has been shared.
Yeah. Thank you.
Yes, the PPT will be shared with all the participants if it will be given by the experts after the
Yeah,
completion of
sure.
this course.
Okay.
No problem, sir. You can just simply cross your.
Yeah, yes.
Yes, sir.
हेलो गुड आफ्टरनून अब्दुल जी
Good afternoon, sir. How
कैसे
are you, sir?
फाइन फाइन एम आई ऑडिबल अब्दुल जी
Yes, sir. Yes, you are audible.
ओके ओके देन वी शुड स्टार्ट एट 3:30 पॉजिटिवली ना
Yes, sir.
ओके
Participants are
पार्टिसिपेंट्स हैव ज्वाइन अच्छा हाँ फ्यू
part.
पार्टिसिपेंट्स हैव ज्वाइन आई जस्ट some of the participants have already joined okay
Yes, participants are joining, sir. We will be starting shortly.
अच्छा ओके ओके एट 3:30
Yes, sir. Sure.
ओके अभी
Yeah, Dr. Amit, I think you
Yeah,
can
yeah,
start.
Good afternoon, sir.
Very good afternoon to all of you.
Yes, sir. First, I will introduce you, then you can start your talk.
Okay.
Okay, sir. So, good afternoon, everyone. You all are welcome to this session of OCDT 20. We are about to start this session. We have Professor Amarnath Jha from an institute in Delhi as an expert for this session. Now, I would like to introduce Professor Amarnath Jha first, then the talk will be started. So, Professor Amarnath Jha received his bachelor degree in electrical engineering from Bhagalpur College of Engineering, Bhagalpur University in 1988, followed by his master's degree in electrical engineering specialization in control and instrumentation from University of Delhi in 2001. He also obtained his PhD from the same university. He was holding the position of assistant professor and associate professor. Presently, he is professor in the Department of Instrumentation and Control Engineering. His teaching and research interests are in control systems, process control, mechatronics, and large-scale systems. He is a life member of ISTE. He served as faculty advisor of ISTE in NSIT and ISA student chapter, and under his able guidance, NSIT received Best ISTE student chapter. Dr. Jha published papers in referred international and national journals and conferences. He delivered a series of lectures on mechatronics and also delivered keynote address on related topics. He also organized AICTE IST short-term training on nanotechnology as a coordinator. Apart from that, he was a coordinator for design of MTech syllabus of mechatronics. He is a member of a screening committee of MTech admission and PhD admission committee, warden of the Boys Hostel, and director's nominee for Central Purchase Committee. Presently, he is lab in charge of mechatronics lab and coordinator of Bachelor of Fashion Technology admissions. So apart from academia, he also is an active participant in the field of sports and won a couple of races during the sports day of NSIT. He stood first in 100 meters race for my faculty, fetching gold medal for himself. So with these words, I would like to invite Professor N. Jha to kindly start his talk. Please start, sir.
Okay. Thank you.
Thank you, sir. Thank you.
Words. Okay. So today the session is I will present my on model order reduction technique and its applications. Okay. That is the sessions for today's. So in this first topic, there are some outlines of the presentations, the techniques of model order reductions, development of new algorithm for reduced order modeling of linear systems, applications of reduced order modeling in control designs, and applications in DC-DC converter and servo systems. So firstly, we'll have to explain that what is the model order reductions. Let me explain first that the model order reduction is, am I audible? Hello? Am I?
Yes, sir, you are audible. Please continue. No problem.
Okay. So model order reduction is a branch of a system and control theory which reduces the complexity of a large scale dynamical systems while preserving their input-output behavior to the possible extent. In other ways, model order tries to quickly capture the essential features of structures. This means that at an early stage of the process, the most basic properties of original model must already be present in smaller approximations. And this is the graphical illustrations of model order reduction, how the complexities are reduced in different stages. Then next is this is first stage is the physical systems. The physical system is then represented in mathematical models. This is the linear represented by ordinary differential equations, and then by using model order reduction technique, we are dimensionally reducing the order of the systems, and then it is used for analysis, simulation, and controls in optimization techniques. Okay? Then is the advantages of model order reductions. What are the advantages of model order reductions? So these are the advantages that model order reductions reduces the complexity of controllers, because we know that as the order of the system is large, the order of the controller will be also the large. So the complexity, if we have the hardware systems, then the complexity can be very, very high in case of higher order systems. So if the order of the system is reduced, the controller's size is also reduced, and in this way it reduces the complexity of controller. Then the design cost reduces, because the order is reduced, so the cost is also get reduced. The speed of operation and restoration of the controller improves. Computational efforts also reduce, because the size is reduced, so it takes less time to solve the problems, to analyze the problems, and then it becomes very simple to analyze the problems. So simplify the understanding of the systems, and it overall the efficiency of the system is improves. So these are the various advantages of the model order reductions. Then the classifications of the model order reductions. The model order reduction is classified in time domain as well as in the frequency domains. So in the time domain, this system is represented by, for higher order single order systems, single input single output system can be expressed by a GS, which is the numerator by denominator polynomials, and these are the coefficients A0, A1, A2, M, the numerators B0, B1, B2, Bn. So for proper realizations, the numerator power should be less than the denominator power, that is M should be less than and equal to N. Suppose there is a need to determine reduced order model of above higher order systems, and let R be the reduced order model, then reduced order model favor systems can be written as GRS. This is the reduced order model, and it is also in terms of the numerator and denominator, where C0, C1, C2, CQ are the coefficients of the numerator polynomial of reduced order, and D0, D1, D2, DR are the coefficients of denominator polynomial, where the Q should be less than or equal to R. That is, the numerator polynomial, order of numerator polynomial should be less than or equal to R. So the main purpose is, this is the GRS is the reduced order transfer functions, and GS is the main transfer functions. So the main purpose is to determine the coefficients in such a way the response of original model is equivalent to GRS. That is what is the objectives of the model order reductions, that the original transfer functions and the reduced order model should match. If you take the response of these two, this would match. The main feature should be preserved. Right? As how we represent in the time domain analysis. In the time domain analysis, for a linear time invariant system, we know that this is the state space representation of a systems, which is represented by x dot t equal to axt plus but, and yt equal to cxt plus dut, where xt is the state matrix, and ut is the input matrix, x and out yt is the output vectors, where a, b, c, d are the matrices. So this is the state space representations. If you take a reduced order model, then we have put a bar here so that it can differentiate from the original system to the reduced system. So this is represented by here x bar dot t equal to a cap xt plus b cap ut, and yt equal to c cap xt plus d cap ut. So these are the coefficients here. A cap, B cap, C cap, these are the matrices here. Okay, but these matrices are the reduced order. Okay, so this how we can see is that if you take the transfer function of the original systems, GS, that is represented in terms of ABCD parameter, that is transfer function can be represented as C equal to Si minus A inverse D plus D. Reduced order model G cap S is also similarly in this way. And the main property of the reduced order, main property is that the norms of GS and G cap S should be within the prescribed error band. That is what is the objectives of the model order reduction techniques. Then there are various methods in frequency domain, the techniques for the model order reductions. Radial type approximation methods, model reduction using route stability criterion, model reduction using route table criterion, model reduction algorithm based on stability equations, and mixed methods of approximation. These are the various techniques for model order reductions in the frequency domains. Okay. Similarly, in the time domain methods, the aggregation methods, singular perturbation based approach, and error minimization approach. These are some of the techniques. There are so many techniques, but some of the techniques here we have to just explain about the basic concepts. Few algorithm and methods on modeling reported by various or some of the prominent authors which has reported in the model order techniques are the Paddy techniques, which was developed in 1986, Core techniques in 1979, Bootman's method in 1982, Pepoi method in 78, Newton method in 75, Paul methods, V. Krishnamurthy's method in 78, and analytical technique based on Gauss-Gorian theorem. This was proposed by Dr. Y.V. Hussain, who was my guide during the PhD. So these methods, the basic concepts about these methods, the aggregation in the time domain method is the basic concepts about what is the aggregation method. So this technique has been proposed by Akoi in 1968. This aggregation term is appeared in economic literature before arriving in control literature. Here the model is derived by aggregating the original system state vector into a low dimensional vectors. So that's why it is called the aggregated methods. So the aggregated model is of the lower dimension as compared to the original model. Division technique of model reductions. This technique has been proposed in 1966 by E.J. Davisons. This approach is based on dominant eigenvalue approach. The idea of this method is to neglect the eigenvalues of original systems which are farthest away from the origin and retain only the dominant eigenvalue. So this technique is basically to reduce the model based on the eigenvalues, and eigenvalues, the eigenvalues which are far away from the origin, that can be neglected, and those eigenvalues which are near the origin, that or the dominant eigenvalue can be retained. So this method is applicable to any large, linear and multivariable systems, but it is the time consuming for higher order systems. Then in frequency domain method, this is very simple approach proposed by the V. Krishnamurthy and Seshadri. This is based on the route criterion. So this method of model order reduction is based on route criterion. In this method, the technique which is applicable to check the stability of system is same as applicable to reduce the model of the systems. In this approach, reduced order model is determined by applying route criterion to both denominator and numerator polynomials. That we can explain later on with the help of some numerical examples. So this method is very elegant and applicable to unstable system also. Then truncation method, this is the very simplest method as proposed by Weiss-Ames, that in this method, reduced order model can be determined by truncating higher order terms particularly for lower order system. However, higher order systems, reduced order model will be unstable if original reduced order model is stable. So this is the lacuna of these systems, that if the order is of the higher order, reduced order model may be unstable if original system is stable. But for a lower order systems, this gives a better result. And moment matching method of the model order reductions. This method is based on matching the time moment of full model's impulse response to those of the reduced model. So, and this is important approach for a model order reductions. So this method has come to the literature in 75. This method is based on the concept of route criterion. It is called the route approximation method. The basic idea of this method is to develop route array for original system and then construct the approximate in such a manner that coefficient of route array agree to a given order. In this method, if original system is stable, then reduced order system will also be stable. So this is another method, T.N. Lucas approach of model reduction using the factor division methods. Then, so these are some other methods also. This is for a Jan, Paul, and Elamre approach of model reduction for a multi-variable systems. Then is the model order reduction by differentiation method. This is also very simple method. This method is proposed by Gutman. In this method, model order reduction is based on the differentiation of a polynomial. You take a polynomial, you take the differentiations, but in this approach, reciprocal of numerator and denominator polynomial of higher order transfer functions are differentiated suitably many times to get the coefficient of reduced order transfer function. It is observed that the method is simple to understand. Then this is also very important methods, that is the continued fraction expansion. Using the concept of continued fraction expansions, Chen and Say have first introduced the concept of model order reductions for linear time invariant systems. The beauty of this technique is that there is no need to calculate the eigenvalues and eigenvectors, and it also retains the essential feature of the systems. Based on this, modified results of a model order reduction have been reported. Then is the mixed methods. Mixed method means you take some methods from the stability equation methods and modify core methods. That is called the mixed methods. So by using all these techniques, we can have the model order reductions. Then this is model order reduction for an unstable system. If the system is unstable, in that case, how can you find a model order reduction? In that case, this approach proposed by J. Yang. In this approach, model reduction of unstable system can be carried out such that the translation information as plane preserve the input-output property of the systems. Using translation information in the S-plane, it is possible to modify the stability of the system without losing input-output informations. However, balancing needs that the model is to be asymptotically stable. This requirement will be satisfied by computing controllability and observability gradients. Okay. So if you satisfy the complete controllability and observability gradients, this method is good, balanced. And is the Day approximation. It is very important methods for model order reduction techniques. In this case, it was proposed by Weiss-Emmons that this approach is based on the matching a few coefficients of power series expansion about S equal to 0 of the reduced order model with the corresponding coefficients of the original model. So this approach was first proposed by Weiss-Emmons. Consider a function, this is a function fs which can be expressed in finite series, that is C0 plus C1 can be expanded. C0 plus C1s plus C2s square plus C3s cube, that will be continued. Okay, so this is a this is a functions, and there is another rational functions which is expressed by un upon vns, where un vns are the mth and nth order polynomial in S respectively. So one is the functions which can be expressed as infinite series expansions, and other is a rational functions which is in terms of the numerator and denominator polynomials, where the numerator polynomial is less than the denominator polynomial. So these two functions, the rational function is said to be a Pade approximant of fs if and only if the first n plus n terms of the power series expansion of fs and un by vns are identical. If do see it here, this is the power series expansion of any functions where c0, c1, c2 are the coefficients, okay, and other function is a rational functions where um and vns are the polynomials in S domains, and the numerator polynomial is less than the denominator polynomial. If the numerator polynomial is of the power of m, order of m, and denominator polynomial is of the order of n, then the sum of the m plus n terms series expansion of fs and this should be identical. Then this is called the Pade approximation. So the rational functions fs um by fs will be called the approximant of the function fs. Okay? So this is about the Pade approximant. It is very important method in the model of the reduction technique. So in this case, we have considered a problem which is of the fourth order. Basically, so far, in the literature of control systems or the model of the reduction techniques, the authors have reported that the Pade approximation is superior than all other techniques like stability equation methods or Routh stability methods. So this has been shown here that Pade is superior in comparison to the other techniques for these problems, for this class of the systems. But I will show you that I have researched for this one, and I have shown that the Pade is no more superior than the other techniques, whatever the SEMAS has told in this problem. So this problem has been taken from the other. So this is reported by SEMAS. So this is of the fourth order systems. This of fourth order system is expressed here in this form, so that the coefficient, it should be the 1. It is in terms of 1 plus s squared. Okay, so this can be simplified in this form. This is known as G1s. Then you write the numerator and denominator in the Rauthian array type of the array. Okay, so this is the Rauthian array. You have to write this one. So the first row is from the numerator, from the denominator 1, 20, 20.1, 104 coefficients, then 21 coefficient of S3, then coefficient of S4. This is the first row. Then the second row is similarly 19.17, this row, and then you find the coefficients like the Routh tables. You find the coefficient in the first column. Okay, so you will see that here the C0 will be, C0 is 1. The second row column, this is 1. Second row, first column 1. Then this is the C1 with negative sign. Then this will be the positive sign C2. This will be the C3 with negative sign. So alternately positive and negative. That will give you the value of C0, C1, C2, C3. So in this way, you can find by using the Pade approximations the coefficient of numerator and denominator polynomials. So this is expressed as a transfer function of the second order and R1s. Okay. Then by using the same problem, using the Routh stability methods, we take the numerator and denominator, we put in this form, and then find the second order transfer functions. Second order transfer, if you have to take the second order transfer functions, so it will be the coefficient of s square will be this one, coefficient of s1 will be this one, coefficient of s0 will be this one. For the numerator, it should be coefficient of s1 is this and coefficient of s0 is this. So this can be represented by this one, by route tables. This will be the second order. And if you put in this form, this will be s square plus this plus constant. Okay. So this is what is by using the route tables. Then next method is stability equation method. My objective is that as I have told you that the Paddy's, most of the authors have shown that the Paddy's is superior, as Paddy's technique is superior than other techniques like stability equation method and some route tables and or many more techniques. But here I can show you that this can be opposite also, vice versa, that Paddy's is no more superior. And also I have published a paper on that one that I can show you later on. So this is what is the stability equation method. So similarly, the stability equation method, the numerator and denominator polynomials, numerator and you can write the numerator and denominator polynomial. The denominator polynomial can be the sum of the even term and the sum of the odd terms. Okay, so that you have to bifurcate on the basis of the even term and the odd term for the denominator polynomial and also the numerator polynomial, and discard those which are non-dominant. So discarding the non-dominant part, we can get the reduced order model using the stability equation method. So this is also of the second order. So in this case, Paddy is superior as compared to Paddy is superior. You see it here that this is the Paddy approximations, this is the original equations, original model. So Paddy in this case, but when you take the route stability and the route table, there is much deviations. The transient as well as the steady state response is not matching with the original system. So the author has shown that Paddy is superior, but you can see it here also. When you take here, see the time duration is for the simulation period is for 0 to 4.5 seconds. If you take a time duration for a higher time interval, in that case you will see the response like this one. See here the interval we have taken from 0 to 140 seconds. See it here. In that case, this is the original model, this is the route table method, this is the stability equation method, this is the Paddy. You will see that the steady state response is matching. Although there is some deviation in the transient, but steady state response is matching. So this is what I have proposed, this technique, and so I have shown that Paddy method is not superior as compared to existing stability equation method and route table methods. So in that case, if you take the frequency domain analysis also, I have shown that in the frequency domain analysis, for the higher frequency range, you will see that there is much deviations in the magnitude and the phase angle of the original model and the Paddy approximations method. So this is what is that Paddy is not superior, Paddy method is not superior as compared as told by various authors. So that I try to show by my papers. Hello? Hello? Am I audible?
Yes, sir.
Yes, yes, sir. Yes, sir.
Yes, sir, you are
Yes,
audible.
sir.
No problem.
It
Continue.
is because it
Yes,
is
sir.
highly mathematical, highly mathematical. That's why I have given this examples. On that basis, you can have some develop some interest and see how the mathematics is converted into real problems to solve the model order reduction techniques. And one is the very Krishnamurti's result based on the route criterions. I will show you how we can use this. This is the Krishnamurti's result. It is very simple methods. In this case, first we will explain about the Krishnamurti's approach of model order reductions. Let's see it here. I will explain with the examples. Just wait. I will show you later on Krishnamurti's approach. See it here. See here. This is the open loop transfer function of a system. See it here. Because in the denominator, the constant term is missing. So it is the coefficient of constant is missing here. S to the power n, S to the power n minus 1, and S to the power 1. There is no coefficient here. So this open loop transfer system, this function, this system is unstable system as there is one pole at the origin. So how can you find the model order reduction for this system? So what we do by using the Krishnamurti's approach, I have developed solve these problems. For the unstable system, how can you find the model order reductions? But before going to this one, I want to just do the numerical problems so that it will be more explained. See it here. This is the open loop transfer functions. In the open loop transfer function, the coefficient term is missing. So this is the GS. You find the 1 plus GS, that will be the characteristic equation. 1 plus GS is this one. The closed loop characteristic equation is this one. Now this is the fifth order. You find the Raudian criterion. Now you apply the route table for this one. So this will be the route table. Suppose you have to find a second order model, or the third order or the first order. So you will see this is the first column. All this is positive. So if you have to find the third order systems, so it will be coefficient 126.66 S cube plus 191.52 S square plus 212.S1 plus 10 S0. So this will be the third order. Similarly, the second order system will be characteristic equation of second order will be 191.52 S square, 212.90 S1 and 10 S0. So this is the reduced order, first order, second order, and third order characteristic equation. This is 1 plus GS. So if you know the 1 plus GS, you can able to find out the open loop transfer function for the reduced order. So the open loop transfer function for the reduced order is this one, this one, this one, and this one. This is for the second order. This is for the third order. Okay. So this is what is the Krishnamurti's approach. In this case, if you take the step response of the original model and first order model, see it here, you will see that the reduced order model is almost matching with the original model. Okay. If you see the second order model with the original model, it is more matching with the original model. If you take the third order system, it will almost exactly matching with the third order. So if the order of the system is increased, it will be more, the accuracy will be get increased. Okay. If the order of system you can reduce, the accuracy will be least. So this is what is the plot for all the system taking simultaneously. But the thing is, I want to convince you about the Krishnamurti's approach. Okay. V. Krishnamurti's approach is that I am not. Okay. So this is the Krishnamurti's approach. In the Krishnamurti's approach, what we do? This is the eighth order systems. So we write the numerator and denominator. Sorry. For the denominator polynomial, also we write the route table. For numerator polynomial, we also write the route table, and then we find the reduced order model as we discussed in the previous case. Okay. So this is what is the simple and elegant methods that Krishnamurti has taken the numerator. You reduce the numerator polynomial also, reduce the denominator polynomial also using the route tables, and then you find the reduced order model. So this is very simple. The problem here is that, so this is what is the response of the original systems and reduced order model. If you take the lower order model, the matching will be missed. If you take the higher order systems, closing to original systems, there will be more matching. Okay. Here I want to convince you that this is unstable systems. The unstable system can also be reduced using the V. Krishnamurti's methods. Okay, this is what is the beauty. And on this, I have also published a paper that can be shown later on also. Then come to next is my approach to model order reduction using the Gauss-Gorian theorem. By using Gauss-Gorian theorem, this is also one of the technique for the model order reductions. By using this technique, one can use this can be used for model order reductions. So firstly, we have to understand that what is the Gauss-Gorian theorem. What is Gauss-Gorian circles? So in the Gauss-Gorian theorem, it states that all eigenvalues of a given system matrix A exist in the intersections of row-wise and column-wise circles. See here, it states that all the eigenvalues of a given system matrix A exist in the intersection of row-wise and column-wise circles. This method requires that the system matrix A be partitioned into, decouple the system into two subsystems, row subsystems and vast subsystems. Then the Gaussian theorem is used to identify different non-intersecting shapes based on the extreme ends of the circles. And by permutations of rows and then using singular perturbation theory, reduced order model is obtained. So just take it here. A state space representation is given here. This is the fourth order systems. So this is A matrix, this is the B matrix, this is the B transpose here. So this is the column matrix. So this is B transpose, this is the C, this is the D, and this is the reduced order model. Okay. So when you take the reduced order model, you will see that it is matching, almost matching with the original systems. But the limitation of this approach is that this approach is applicable only to linear time invariant system. It is not applicable to linear uncertain system. It is not applicable to non-linear and time varying systems. This is what I think is visible. Is it visible to all of you? Hello?
Yes, sir.
Visible.
Yes, sir. Yes, sir.
Okay. So just see it here. What is the Gauss-Gorian circle? I will come to later on. I will explain the Gauss-Gorian approach. Before that, you see it here. In the Gauss-Gorian circle theorem, the y-axis is interpreted at the imaginary axis. Since the roots of characteristic polynomial allowed to be complex number, they take on the form of x plus iy, where I is the square root. See it here. This is the matrix m equal to third order 3 by 3 की matrix है. These are matrix and these are the diagonal elements. Diagonal elements क्या है? 1 minus 5 minus 3. Okay. So how can you draw the Gaussian circle? You can see it here. So take the diagonal matrix 1 minus 5 or minus 3. So this will be the center will be the diagonal element. So 1 minus 5 minus 3 will be the center, and the radius will be the row wise summation of the row wise of the rest of the element or the column wise. So see it here. So in this case the radius is 0 plus 7, so radius is 7, or this one center radius is 1, sorry, center is 1. If you take the center at 1 0 and radius of 7, you can get this circle, bigger circles. Then you take the second row, the center is at minus 0.5 and minus 0.50 and radius is of 2. So that will give you this circle. Then you take the third row, the center is at minus 3 and radius is of 8. So minus 3 पे 8 radius will be 9. This will give you the circles. So we'll see that the eigenvalue lie inside the union of eigenvalues will be here inside the union of the circles. This is what is the Gaussian circle says. So come to here, it will be easier here to understand the basic approach of Gaussian approach. See it here. The reduced order modeling of a state space system using above basic rules and similar perturbation theory. We identify dominant and non-dominant eigenvalues of the system. Suppose the matrix is where A11, this is the matrix, and this is the magnitude A. So by applying the conventional approach of Gaussian theorem, it says that the modulus lambda minus AII should be less than Ri, less than and equal to Ri. It means, what is the lambda? Lambda is the eigenvalues. Okay, so from above equation, you can see that A11, A22, A33, like that is the diagonal elements. Okay, and this is the sum row wise and this is the column wise. So see it here, lambda minus, see it here, lambda, what is the lambda minus A11 mod should be less than Ri. So what is Ri? Ri is equal to summation of Aij, means you take the lambda is the eigenvalues, so lambda minus Aii, this should be equal to R1, that is the row wise summation of A12, A13, A11 like that. So if you take the eigenvalues lambda 1, so lambda 1 minus A11 should be less than equal to A12 summation of A12, A13, A1. Similarly, lambda 2 minus A22 should be less than and equal to A21, A23, A21 like this. So this is what is the Gaussian approach, that lambda minus AI should be less than equal to R1. So by applying the conventional approach, we cannot find the model order reductions. But if you apply a modified approach that we have applied, then we can use the Gaussian theorem for model order reduction. By conventional approach, we cannot find the model order reductions. You can see it here also. This is what is the conventional approach. Conventional approach में summation row wise लेना है और एक बार in one time it should be in the row wise, in other time it should be in the column wise. Okay, so just see it here. So apply conventional approach of Gaussian theorem for A transpose. A transpose means column wise. Okay, so in this case, if you take this Zhuang approach, then you can get the model order reductions by using the Gauss-Bonnier theorem. So just a minute, I'm not able to show you. Sorry. Just see it here. I want to convince you that these are the diagonal elements. The diagonal elements 1 minus 5 minus 3, the diagonal elements should be very close to the eigenvalues. Okay? So it says that the difference between the diagonal eigenvalues minus diagonal element should be less than the summation of this one in the row wise or in the column wise. Hello?
Yes, sir.
Yes, sir.
Yeah. So this is what I want to convince you, that when we take the Gauss-Bonnier approach, we have to find the Gauss-Bonnier cycle, Gauss-Bonnier circles, and the Gauss-Bonnier circles. On that basis, we say that we can find, by using the simple row-wise and column-wise techniques, we cannot find the model order reductions. Because in that case, I can show you that, see it here. When you take the problem, this is the problem. Just see the numerical problem, then it will become very much clear. This is the state space representation. This is of the third order system. So ABCD matrix is here. So you find the step 1 here, you find the row wise applying Gauss-Bonnier theorem to A. So lambda 1 minus lambda 1 minus lambda 4 minus lambda 7. So lambda minus 1 equal to lambda plus 1. So this is lambda plus 1, this is lambda plus 4, and this is lambda plus 7. So when we take a first row, in that case, lambda plus 1 is less than, lambda plus 1 is less than the summation of the rest elements. So this is 1.9 and 0.56. So mod lambda plus 1 is less than 2.46. Similarly, in the second row, lambda plus 4 is less than the summation of 1.1 and 7.9. That is, lambda plus 4 is less than 1.89. And third row, lambda plus 7 is less than 2.4. So if you find a Gauss-Bonnier circle for this one, you have to find the Gauss-Bonnier circle. You will see that this is the Gauss-Bonnier circle. These circles are intersecting to each other. When it is intersecting to each other, you cannot find the exact eigenvalues, the dominant or non-dominant eigenvalues. You cannot separate the eigenvalues. It will be the combined, it will be the mixed. So, but if you take this approach simply, you cannot find the model order reduction. Okay, so this is the conventional approach while we take the Gauss-Bonnier circle using the row wise. Then the next is the column wise. When you take the column wise means this one. Take 0.1, 1.1, 0.3, that is 1.4 in first column. In the second column, this is the 1.9 and 2.1. So this will be 4. In third column, it is in the third column it is 0.56 and 0.79. So you can get the step 2, that applying Gauss-Bonnier theorem to a transpose, lambda plus 1 is less than 1.4, lambda plus 4 is less than 0.4, and lambda plus 7 is less than 1.35. So applying this Gauss-Bonnier theorem to column wise, the Gauss-Bonnier circles for equation 3 is given here. Again, we cannot get the independent separate eigenvalues. Okay. So in that case, we will not able to find out the eigenvalues separately. So for that, what we did, we apply the another method, that is the Zhuang's approach, and in that case, In that case, this is the John's approach, that the above matrix now is lambda minus A11 should be less than equal to rho into mod A minus Q, where rho is the spectral radius of the matrix. In this case, we have to express the lambda minus A11 in terms of the spectral radius. It should be less than the rho into A minus Q. What is A? A is the system matrix, and Q is the diagonal matrix. Q is the diagonal matrix. Q1, Q2, Q3, like that. So then let us take rho into A minus Q, you take as a K. So then this above lambda minus A11 should be less than equal to K. So in this case, you find the Gaussian double equation can be simplified now in this Gaussian D3. So by using this one, you can find this one, D3. And then you take this one. This is what G4 is. Gaussian bound can be determined by using this equation, that lambda plus A11 should be less than S1, lambda plus A22 should be less than S2. What is S1, S2 and S3? It is the minimum of R1, C1 and K. Okay, R2, C2 and K. Okay, you know what is the center, what is the radius, and what is the K. K you have find from the here. So in this way you can find the minimum. So when we take this one, in that case you can get the Gaussian circle by Joan approach. You can this one. Once you get these positions, then we will, by using the other identity, by using the so this is the inference, that it is seen that all Gaussian circles are non-intersectings, and therefore each circle represents only one eigenvalue. Therefore, we can easily identify slow system and fast systems. When you know the slow system and fast systems, then on the basis of similar perturbation technique, we can identify the slow system and fast systems and find the reduced order model. And for that, the next step is that we use the permutation matrix. By using the permutation matrix, we separate the dominant and non-dominant parts, and we get the reduced order model. So this is what is the original and reduced order model. So just I want to convince you that when you find these three are the graphical representation, in one case we will see that these circles are intersecting, so we cannot get the separate eigenvalues in one case. In another case, we get this type of the circles. Again, we are not getting. It is the intersecting the circles. But when we approach a new approach, from these two figures, it is observed that the Gaussian circles are intersecting. Therefore, it is difficult to decide what one is a slow system and which one is a slow system, which one is a fast system. Therefore, all existing methods based on Gaussian theorem fail to determine reduced order modeling of the systems. Then is the proposed approach what we have used using these techniques. We get the separate Gaussian circles, and the inference is that it is seen that all Gaussian circles are non-intersecting, and therefore each circle represents only one eigenvalues. So we can easily identify slow systems and fast systems. So separating dominant and non-dominant parts, we get the response of this one. And if you take this by proposed approach, we see that the integral, the performance parameters ISE, IAE, ITE is least as compared to the truncation method, route stability methods, and stability equation method. So escape करते हैं. Just see This is the practical problems I have taken. Experimental results for application of proposed approach based on Krishnamurthy's criterion to position control system. So this is the field control mathematical model. This is servo motors, field controls. So this is the transfer function between position and fields. So you will get this one. This is the unstable systems. We reduce it by using Krishnamurthy's approach and find the step response. We will see that it is almost reduced order model and original model is matching. Then we'll come to the applications. Hello?
Sir, you are audible.
Yeah, okay, good. So, step is now we'll come to the application part. This is the application using the position control systems based on Krishnamurthy's criterion. Then we come to reduce order modeling of DC-DC converter. We have used the DC converter. We take the model order reduction of this one and using model order reduction, different model order reduction techniques, we see the response of this one. So firstly we will discuss about the concepts about the DC converters, DC-DC converters. So see it here, the model order reduction technique for cup converters. We know that the modeling of DC-DC cup converter is non-linear due to diode and power switch. However, linear model is obtained by using a state space averaging technique, which gives a fourth order model. The fourth order converter model will be reduced to third and second order using various model order reduction techniques. Then comparison of these techniques will be carried out in the time domain and frequency domain using MATLAB environment. So this is the modeling of DC-DC cup converters. Cup converter, the seat here. Cup converter contains 4 energy storage elements, 2 inductors and 2 capacitors, which gives fourth order model, whereas the order of buck and boost converter is second. So see it here in the diagram. This is what is the switch here. These are the 2 inductors and 2 capacitors. This is the input voltage. This is the switch. The switch can be the MOSFET or the FET or the transistor, any having some frequency. We have this, and this is the diode. So in this case, we know because it contains the diode, so at the switch, so it will become a non-linear. It is not a linear devices. So we use the state space averaging techniques for this one. So let us say what is the state space averaging of a system. It says that x dot equal to, if the system is linear system is represented by x dot t equal to axt plus but and yt equal to cxt plus eut. For continuous conduction mode, DC-DC converter operates in 2 circuit states in one switching period. That is, in one switching period, on time and off time. So active switch is on for a period of time, a small d, capital T. D is the duty cycles and T is the time period for switch on period, switching on, and switch off period is 1 minus D into T. So T is the switching time period and D is the duty cycle. So see it here. So this is the current here, inductor current, voltage across the current. We take the variables, voltage across the capacitor and current through the conductors as variables. So this is the IL1, and IL2, these are the current through the inductors, then voltage across capacitors. One is VC1 and this is the VC2. So this is the diagram for the DC-DC converters. In this case, the polarity here is just the opposite seat here. This has the opposite voltage here. The output will be just opposite to the input. And this is the switch here. So capacitor voltage and inductor current are chosen as state variable. The state space equations of the converter of two circuit states are given below. When switch is on for a period of time 0 to dt, this will be the equation for a switching time. The system will become x0t equal to a1 xt plus b1 ut, yt equal to cn xt plus un ut. This is for a on time period. This is for an off time period. This is for an off time period. And then what happens? We take the average of these two. Okay? That will be, when we take the average of these two, that will be a non-linear system. So we have to linearize that. We have to linearize about some operating point, and that operating point will be a DC part, and there will be two parts in that case. One will be the DC part and other will be the small signals. So in that case, it can be the nonlinear part can be resolved into a DC part and a small signal part. So just see it here. When the circuit is on, what happens in this case? The converter case, when the circuit is on, in that case, when this switch is off, suppose this switch is off, in that case the voltage will appear across this one. This voltage will appear across this one. Okay, and because it is the this will be at the negative, so this diode would not conduct. So this will the voltage, the capacitor will be fully charged. Now when this switch is on, in that case it will be closed here. See it here. When this is closed, and then what happens? This will go to whatever is the voltage. That voltage will go. This capacitor voltage will be discharged through this capacitors and this resistance. So the charging current will be passing through this one. Okay. So this is the switching on time period. When it is the off time period, in that case, this capacitor will get charged. The diode, whatever is that, the diode would conduct, and again this will be the path. So this current, the capacitor will again discharge through this voltage and this one. So this is what is the conduction mode, switching on period and off period. But main objective here is to determine because this is the non-linear systems. So here you have to linearize. Some small perturbation around operating point is introduced here. So this is the operating point, this is the DC part, and this is the AC part. Okay. So this is the small signals, and this is very, very large as compared to this one. So we can neglect also this one. This is very, very large. So this nonlinear system can have the two parts. One is the steady state value, other is the small signals. When you take the Laplace, you can get this output x dot cap t equal to axt, but and bd dt. Means this will be a function of state in input B and disturbance. This is the duty D. Okay, this is the duty. So in these terms, it can be expressed. Substitution you can get this one. When you take the Laplace transform after simplifications, you can get this. This is the output with respect to the cycle. This is the output with respect to the input voltage. So because we know C, we know A, we know B, we know E. Detail is not given here, but everything you can calculate. Okay, when you calculate, you can get the value of A. A is the equivalent value of both A1, A2, B1, B2, C1, C2, E1, E2. So this will be ABCD. With a state space matrix defined, control output transfer function can be defined like this one. Just a minute. So with a state space matrices defined, control to output transfer function can be defined like this. So this will be the transfer functions. This transfer function is between output voltage and input duty cycles. In that case, you will see that it is of the fourth order systems. Okay. So if you take the value, substitute the value, we have taken the value of L1, C1, C2 and duty cycles, then we get this transfer function model of the converter. Okay. So when it is of the fourth order, then by using the different techniques, using the route approximation method, truncation method, Payday approximation method, we find the response of original model with the reduced order for a step input. This is the step response. Then response of original model reduced order using truncation method. This is what is the route approximation method. This is by truncation methods, and then is using the Payday approximation method. These are the referred journal. Thanks. Hello.
Yes, sir. Thank you.
Thank you.
Yes, any participants? Question, please.
Just a minute. Yes.
Hello, sir.
Yeah.
Sir, are these techniques anyhow related to system identification?
Pardon?
Sir, can we use these technique for system identification?
Yeah. You can see the paper. There are numerous papers on the system identification also.
Okay, sir. Thank you, sir.
Sir, hello.
Yeah.
Sir, what about order reduction in case of MIMO system?
Multi-input, multi-output systems. Yeah.
Yes.
Yeah. We can
Yes, sir.
reduction, but the expert, I am not expert for the multi-input, multi-output systems. Dr. Afzal is the one of the authority for the multi-input, multi-output systems. So he can explain in better way whether he has taken your expert lectures or not, that I don't know, but he can guide you in better way. He can explain in better way for the multi-input, multi-output. But we use for the multi-output system also, model order reductions.
Okay. Thank you, sir. Thank you very much.
Yes, any other question, please, participants? There are a number of techniques available in the literature for the MIMO system also, and in fact, existing techniques has been extended for the order reduction of MIMO systems.
So,
Yes. Yes, Abhishek.
for the multi-input, multi-output systems.
Yes, sir. Yes, Abhishek is there. Okay. Okay, then thank you, sir. Thank you so much for your expert lecture, and providing this depth knowledge about this model order reduction and covered so many techniques in a short span of time. That is really very good. Your time management is very good. Thank you so much, sir.
Thank you, Abdulji. Thank you giving me this platform to share my ideas, my views with you people. Thanks a lot. Thanks a lot, Dr.
Okay, sir. All the participants are requested to please fill the feedback form which has been provided in the chat box. Thank you. Thank you all.
Thank you, sir.
Thank you. Thanks.